Talk about demonic programming. I was going to say TDD, but I guess demonic programming.
Yes,
By now.
well, it's been determined online, just not in physical reality. So yes, I'm going to be talking, basically, this talk is the extension of Prakash's talk, which I was very pleased when you gave that talk, because I was like, brilliant, I don't have to introduce my talk. I can just say what Prakash said about doing semantics for physics, we've done in one example. So what I'm going to talk about is some work with Samson that we did on taking the logical structure of a certain class of, or a certain set of operations that you can get in a very basic theory of thermodynamics, and turning it into a programming language complete with its own semantics that you can actually do computer science with in order to do physics. So we've proved things about physics using the computer science tools of things like formal verification. So as Prakash said, I should put this way, that there's many similarities between the logic of semantics and the way physicists do physics. And I would say yes, but there's also an awful lot of differences in the way that they actually perform physics. So with physics, you start off with these laws of nature and equations, often differential equations, and you derive solutions from them. And that can be using more or less black magic, it feels like, at certain points. There's nothing in the equations themselves that tell you about their own applicability. That's where the physicist comes in. Whereas with programming, you sort of start from the ground up. You've got a syntax, you've got a semantics, you can derive allowed statements from that, and then if you're doing things like verification, you find invariants. So those are two quite different ways of looking at a system, and it's not immediately obvious that they might be useful to put the laws of physics into a programming style of logic. And part of the reason for this is that when you look at programs and program logics, it's very, very logic-y. It's all, I don't know if that's the word it now is, it's all, you can go from one set of statements that's true to another set of statements that's true, and there's very little arguing about it. Whereas physicists have arguments all the time. And you know, you've got this set of equations and you argue about how you can apply them. And sometimes you have a theory that is a set of equations, and those equations don't necessarily relate to each other. And we find this in quantum mechanics. That's kind of a canonical example with the Born rule, which is that the mod squared of the amplitude of the wave function is equal to the probability that you find in a measurement. Now that is completely independent of the rest of the equations of quantum mechanics. But it's really important because that's how you get probabilities out, that's how you derive things like no signaling. And there's nothing in, if you like, the laws of quantum mechanics that tells you when you apply that. So you have physicists who just somehow know when you apply it, and physicists argue amongst themselves. And at the moment, there's been no way to formalize that process. It's simply you put a bunch of physicists together and they argue it out. And so how could we take that process of argumentation around laws that are agreed on and formalize it? So this would be to try and do the physics equivalent of what you do in automated theorem provers for maths. So things like Isabelle and Koch. So you can see from that it's hard enough getting maths into that kind of logical structure of what mathematicians actually do, it feels like, good luck doing that with physicists. We're even worse. So operational theories, though, are a place where we could have a crossover, where rather than this top-down, you've got laws of nature and equations that you have just sort of dropped from the sky, and how on earth could we relate that to a syntax and a semantics? Well, what if we looked at theories where we just have allowed operations, and we're trying to compose those allowed operations? And we will know what equations those operations satisfy, but we're building up our physics rather than taking it down from the top. And that's what we've done with this example of very, very basic single particle thermodynamics. And here's the reference. So, in view of the time, I'll just say very briefly, there's this guy who I love. I've just come across him. He was a 13th century computer scientist. Only because he lived in the 13th century, they called him a mystic. And he was, in fact, the first person that I've come across who tried to do this. So logic in his day was syllogistic logic, and it was very much involved in the language and can you take propositions to other propositions, whereas he wanted to find out about nature. And so he tried to come up with essentially a process logic for all natural science, not using any of those terms, obviously, because he was in the 13th century. But that's what ultimately this, what I'm about to present is pointing towards. This idea of moving away from starting maybe with axioms or with laws of nature that come down from the top, and can you formalize the processes that happen in physical systems and that give rise to physical laws. So what's the system that I am talking about? I said it was very, very simple thermodynamics. Single particle in a box. And you would think this would be completely boring and there was nothing to say about it. But believe it or not, this single particle in a box has been argued about for coming up to 200 years. What can you what states can you get out of this? What can you do with this? And it's really, really simple because you've got a single box, a single particle, you've got a partition that can come in and out, and you've got pistons that can slide in and out. And the equations that they satisfy are very simple. So we're surrounding it with a heat bath at temperature T, which means T is not a variable, which is great. We like not having variables in physics. And so we've got the pressure of this single particle rattling around, the volume of the box, which is either 1 or a half, depending on whether you've got the partition in, and there's an entropy. And so entropy is a measure of the disorder of the system. It's this moderately horrible equation. So x is the probability of being in the left-hand side, 1 minus x the probability of being on the right-hand side. And these are the two equations that govern the motion or govern the state variables of the particle in the box. So you'd think that was, it's obvious what you can and can't do with this. So there's also two, if you like, big law, there's one big law and one postulate. So the second law of thermodynamics, you've probably heard of it if you haven't heard precise formulations of it. No net extraction of work without an increase of entropy. That's one way of formulating it. You probably heard entropy does not decrease over time. That's another way of formulating it. And then for the purposes of this talk, I'll talk about Landauer's erasure postulate, because that's the way into what we're doing with this system. And so what Landauer suggested is that you can think of this particle being on the left or the right as a bit. Maybe 0 if it's on the left and 1 if it's on the right. And he postulated that if you want to erase a bit of information in the system, you have to increase the entropy by k log 2. Postulate's not been proved. So where we come in is that people have been trying to take this very simple particle in a box and prove whether or not Landauer's postulate is correct, just for this system. Remarkably, that is incredibly difficult to do. And just to give a flavour of just one set of discussions that people have had about it, these guys, Norton and Ladyman, I'm not going to go through this, but this was a great big ding-dong they had that produced, mountains of paper. It's a great way to get lots of publications, get in an argument with someone and then argue, back and forth. If anyone feels like doing that, see me afterwards. So essentially, one side was saying you can't, unless Landauer's postulate is correct, you're going to violate the second law of thermodynamics. And then the other guys were saying, oh, well, you violate the second law of thermodynamics with those basic piston and partition operations anyway. And then they were going, oh, no, you don't. Oh, yes, you do. And it was rather a Punch and Judy or sort of kind of a spoiler duplicator vibe going on there. But there was no closure to this because they just kept on going back and forth. And James Ladyman actually gave a talk at Oxford, and that's how we got involved, because Sampson came out of the talk going, I just don't understand these philosophers. Why don't they just formalise their system rather than having all these arguments about it? So that's what we did.
You didn't stop the argument?
They've gone on to talking about quantum fluctuations, which is code for they've given up. I feel like I'm giving away physics secrets here. So the basic points of contention are, can you use those basic operations to violate the second law of thermodynamics? You'd think that was easy to prove. Hadn't been proven before this. And can you set it up so you can prove that whenever you erase a bit of information in this system, you increase the entropy? And can we in fact formalize these two statements to be a little less waffly? So there's a very, very basic set of operations. Let's formalize them as an operational semantics. So we're just going to take the allowed operations in the system and make them formal. So first of all, we have to formalize the system itself. We have to give a set of configurations and state variables. So what we're going to do is extract out the logical structure of this system to try and sort of take a step back from the physics and just look at it as a system of what can you and can't you do in this system. And how do we write that? Well, first off, we need to define the state variable. What's the minimal set of information you need to describe the physics of that box system? It's actually this. So you need to know the probability of the particle being found on the left-hand side of the box, because 1 minus it gives you the probability on the right. And we've actually just restricted to 3 options. Either it's definitely on the right, it's definitely on the left, or we don't know where it is with 50-50 probability. Is there a partition? Is there a piston? Yes or no? Those two, A and I, are Boolean flags. And then W, the total amount of work extracted from the system. This is discretized. Just the physics of the system tells you it's discretized into units of kT log 2. That's it. You can convince yourself if you really want that that will give you all the physics. Now, we want to be able to describe things that you can do to those state configurations. So we need a syntax. And this is, I'm not going to have time to go through this properly, but this is the way that we can get statements. And essentially the statements are about these fields. they're statements about the state, probability of being in the left, whether there's partition, whether there's piston, and what the work unit has iterated to. Now, the important thing here is these are how we compose our statements. So we've got the normal, if you like, sequential composition, but we also need this, which on the next slide, when we get to the semantics, we'll see is probabilistic composition. And we've got an if then else, and everything else is pretty. This is based on the while language, so it should be fairly straightforward. Now, these are the interesting ones, the operational semantics. So what have we got? Well, like I said, everything's pretty much normal. This is sequential composition, do one operation and then another and then another. Here, we've got 50-50 probabilistic compositions. So S1 compose S2 means that with probability a half you do F1, S1, and probability a half you do S2. So what do the basic operations look like if we formalize them using this language? So the first allowed operation, you can insert a partition. And what that does is it sets the partition flag to true. It's just an assignment statement there. Remove the partition. So I'm going to go reasonably promptly through this. So if there is a partition, then if there isn't a piston, then your particle becomes completely delocalized and the flag of whether or not there is a partition is false. So this is just giving you an idea that you can describe completely the behavior of what happens when you do these operations. Remove a piston. Depending on whether or not there's a partition, you iterate the work counter, whether it's giving you out work or not. And the same for removing the partition to the right. Inserting a piston, slightly more difficult. I'm not going to go over why. If you want to ask me afterwards, I will say why we have a few extra things in here. But this is where our probabilistic composition is coming in. So this is basically formalizing all the different things that can happen if you insert a piston, depending on where the particle is, whether there's a partition. But this is all derived, these are just the behaviors that happen according to the laws that govern the system. So now we've got this complete set of allowed operations, these 6 allowed operations. Now we can start doing verification on them. So the first thing we want to do is find a computational invariant. So this is not a physical quantity, but a statement. It's a predicate that if it is true before any operation, then it is true after it, and that is also valid through any composition of these arguments. So there is something there's something called Hall logic that enables you to prove this. The proof is 3 pages long. I am not intending to give it here. I can show you it afterwards if anybody would like to see it. But you can take a proposed invariant statement and you can prove using Hall logic that it is an invariant statement for the system, that any composition of those basic operations will preserve that invariant statement. Does anybody want to take a guess what the invariant statement for this system is?
Second law.
That's what you'd think, isn't it? It's almost the second law, and it may be the second law in disguise, but that's the invariant statement. So, what the hell are these? These are 2 different types of entropies. And please, if anybody has seen this entropic quantity here, yell, tell me. I keep on asking people, what is it physically? If you put a minus sign in there, it becomes the Halevo quantity. But it's not the Halevo quantity. It's somehow some form of generalized entropy. So an easy way of seeing what the difference between those 2 entropies is suppose we have 2 computational branches That's what the probabilistic composition gives us, is branching in the computation. And in one of them, we know that it is definitely on the right, and in the other one, we know it's definitely on the left, the particle. Then in both of these, the entropy is 0. So the average entropy is 0. So that's the first of the two terms. But the entropy of the average is k log 2, because the average of x is a half. So if you add the two up, then you're somehow getting both the entropy within each branch and the entropy across branches. Another way we could possibly think of it is that the entropy with the probabilities within a branch are somehow the epistemic probabilities. They're the ones that are known, and the probabilities across branches are the ontological ones. They're the ones out there in the real world. But yes, if anybody has seen that before or comes across it, please tell me or drop me an email or something. So, what can we do with that invariant statement? That invariant statement is somehow encoding it's telling us something about the law, or is it a law? It's telling us something about what transitions you can do with those basic operations. That's the statement that they all have to satisfy. But we can derive consequences from that, if you like, universal statement. And the first thing we can derive is the second law. So this is the Kelvin statement of the second law. There's actually quite a few statements of it, which is one of the problems in thermodynamics. So this is saying you can't come back to the same configuration and have a net extraction of work. So W0 is the initial work counter and WF is the final. So if all of your configuration other than that is the same, then you can't have extracted work from the system. And if we define the 0 point of the work counter to be equal to this, which we can, it's just a counter, it doesn't matter where we start from, then the invariant is satisfied. And we know then we can just turn the handle on this configuration and it drops out that the final work average across branches must always be less than or equal to the initial. So based on that invariant, with a little bit of extra stuff, so it's not exactly the second law, but you get the second law out as a theorem. You can also get Landauer Erasure out as a theorem of the system. And so what we do is you have to define, and I will go very, very quickly through this, you have to define what measurement and resetting are, because we will define erasure as a measure then reset to a known system. And this is something that people who've been discussing Landauer Erasure have that's the definition of erasure that they've finally come up to, and that's what we find works here. So a measurement takes whatever you've got in your branches, and gives you an exact value. So if you start out with a branch where you've got x equals a half, after a measurement, you've got a definite value. So what a measurement does is it zeroes the average branch entropy. What a reset does is it zeroes the number, or it takes the number of branches to 1. So that is resetting it definitely to the left. So a reset zeroes the second type of entropy. Now we can take the computational invariant and figure out what the work cost of those operations are. If we've got an operation that zeroes this entropy, in order to satisfy the computational invariant, how must the work counter change? And what we find is that in order to keep this satisfied, a measurement must require at least a half kT log 2 of work in order to keep this total below 0. A reset must require also at least half kT log 2 of work. This is when applied to a bit. And so if you take an unknown bit of information and you measure and then reset it, in order to keep the invariant satisfied, you must require at least a work cost that is both of those, which is kT log 2, which is exactly Landauer's postulate. So from the computational invariant, we have out, as a theorem, the second law and Landauer erasure, which is not bad, I think. So, conclusions. What have we done? We've taken physics and we've made computer science out of it, or else we've taken computer science and made it into a process language for physics. I prefer to think of it in the second way around. We've defined these basic operations and the composition between them, found an invariant, and from that invariant been able to derive, if you like, universal laws of what any composition of these basic boxes and operations must and must not satisfy. So that gives us another way of tackling physics. This is completely different in feel and in process to the way that we normally do physics, but it's one that I think can give us quite a lot out the end. Places where certainly I would like to take this is to look at other areas of physics where you can try and define basic operations and to try and take the rules of argument that everybody agrees on, take the formulae and laws that everyone agrees on, and agree on a set of basic operations, and then find things like the computational invariants out of those. So I would love to see what quantum mechanics looks like in this. A couple of brief things. How does this way of operationalizing physics relate to an axiomatization? That's one reason why I think looking at quantum mechanics in this form would be quite interesting, because they feel in a certain sense similar, that you're trying to get down to basic operations and then compose from those. But they are very different, because with an operational semantics approach, you're not saying these are the most basic. You're just saying here is a set. And also with the operational semantics approach, you can change the logic that you use to reason about them. And that leads into the final thing, which is, can we use this to automate physics in the same way that we've automated some of mathematics? Thank you.
Any questions?
I didn't understand why you had to first measure before